Welcome to Chatelier's principle. So, when we want to produce some product, we want to choose conditions that favor that desired product. This means that we need to know how changing the concentration, temperature, or pressure will affect the equilibrium position. Because if we want to make whatever our product is, we usually want to get rid of as much of our reactant as possible, and we want to produce as much of our product as possible. So we want to shift our equilibrium as far to the right as we can. So, for example, when Fritz Haber developed the process for synthesizing ammonia, he found, and again this table is taken from the Zumdahl textbook, this is table 13.2, so he found that at various temperatures, 400, 500, and 600 degrees Celsius respectively, and various pressures, 300, 400, and 500 atmospheres, he found that the amount of percentage of product that he got, the ammonia, which is what he was looking for, varied. And so you can see that at higher temperatures, or as we increase the temperature, for each of our pressures, the amount of ammonia left at the end got smaller. And as we increase the pressure, the equilibrium concentration of ammonia got larger. So, note that in his case, each experiment was begun with a 3-to-1 mixture of hydrogen and nitrogen. So, it would appear then that in order to maximize the production of ammonia, we want to conduct the reaction at low temperature and at high pressure. Unfortunately, at low temperature, the reaction occurs far too slowly for it to be useful, and that means that we have to keep the temperature higher, which means that we're shifting the equilibrium to the left, and we're getting a lower fraction of our product that we want, the ammonia that we want. So, and this is one example of Chatelier's principle. Chatelier's principle says that if a change is imposed on a system at equilibrium, then the position of the equilibrium will shift in a direction that tends to reduce that change. So in other words, the system responds in a way that minimizes the change. It doesn't reduce the change all the way to zero. There's always going to be some shift in, say, concentrations, but it doesn't reduce the change. It doesn't reduce the change all the way to zero, but you end up with a lower change than you would otherwise have. So let's say you have some reaction is at equilibrium. If you change the concentration of one of the reactants, let's say you increase the concentration by 1 molar, the reaction to equilibrium will shift such that you'll reduce the concentration of that reactant. You'll still have more than you had before you added the extra bit, but now you'll have a lower concentration of your other reactant or reactants and higher concentrations for your products. And a similar sort of thing is true for other sorts of changes like change in temperature and change in pressures. If you change the temperature, the equilibrium shifts such that it will tend to minimize that change in temperature. So if you raise the temperature, it will tend to shift towards the side that will tend to lower the temperature again. So for the synthesis of ammonia, again we have 3 hydrogen molecules reacting with 1 nitrogen molecule to give us 2 ammonia molecules. So suppose there's an equilibrium position with these concentrations, 1.197 molar of hydrogen, 0.399 molar of nitrogen, and 0.202 molar of ammonia. And we want to know what will happen if 1 mole per liter of nitrogen is suddenly injected into the system. So we're changing our nitrogen concentration. So we're not changing our hydrogen concentration any, at least at the start. The initial nitrogen concentration now is changing from 0.399. We're adding 1 molar. So now we end up with an initial concentration of 1.399 molar for the nitrogen. The ammonia concentration is still the same. We're not changing that any. So now we have our reaction quotient, Q. Remember, we're not at equilibrium anymore now that we've added this extra nitrogen. So now we have Q, and we plug in our values for the concentration of ammonia and the concentrations of hydrogen and nitrogen. And that means that we end up with a value of 1.70 times 10 to the minus 2. And note that we weren't given the value of K, but we can calculate it from the set of equilibrium concentrations that we were originally given. So before we added any of the extra nitrogen. And we can calculate the value of K, our equilibrium constant, as 5.96 times 10 to the minus 2. So we could figure out the new equilibrium position, but we're going to skip that. I'm going to skip that calculation. I'm just going to tell you what the values are. So the equilibrium position, or the second equilibrium position rather, because initially before we added any of our nitrogen, we were already at equilibrium. So the new equilibrium position 2, has a nitrogen concentration of 1.348 molar, a hydrogen concentration of 1.044 molar, and an ammonia concentration of 0.304 molar. So you can see that after we've added this 1 molar, the nitrogen concentration is higher, but it's not higher by the full 1 molar amount that we've added. You can also see that the hydrogen concentration is lower. Our other reactant concentration had to go down, and the ammonia concentration now is higher than we had before. So this means that when we add a reactant to a system at equilibrium, the equilibrium shifts to the right. On the other hand, if we add a product to a system that's already at equilibrium, the equilibrium will shift to the left to try to reduce that change, to try to eliminate some of the added product that we've added. So, assuming, of course, that by adding the reactant or product, we are changing its concentration. That is, if we add more of a pure liquid or a pure solid, then we don't change the equilibrium position because we aren't changing the concentration of the pure liquid or pure solid. And again, that's because a pure liquid or pure solid don't factor into the equilibrium expression, and that means that changing one of those values isn't going to change, or changing the amount that we have isn't going to change the concentration of that pure solid or pure liquid. It's not going to change the value that we have for our reaction quotient. So we can explain these shifts in terms of reaction rates. So at equilibrium, the forward and reverse reaction rates are equal. By increasing the reactant concentration, we increase the forward reaction rate, and thus we must make more of our products in order to increase the reverse reaction rate and obtain equal forward and reverse reaction rates again. So note that if we remove a reactant or product, we will decrease the forward or reverse reaction rate, and thus removing a reactant causes equilibrium to shift to the left, because as we remove the reactant, we're lowering the forward reaction rate. That backward reaction rate, at least initially, is the same, and that means that over time we're producing more of our reactant again, until we've reduced our product concentration some and produced a little bit more of our reactants. So again, removing a reactant causes equilibrium to shift to the left, while removing a product causes equilibrium to shift to the right. So there are 3 ways to change the pressure of a reaction system involving gaseous components. We could add or remove a gaseous reactant or product. We could add an inert gas, so one that will not react with the reactants or the products. Or we could change the volume of the container without changing the number of moles of gas, so we could just squeeze the whole reaction mixture into a smaller volume or expand it into a larger volume. If we add an inert gas, the total pressure increases, but the concentrations or the partial pressures of our reactants and products remain unchanged. Now this is because, again, we're increasing the total pressure because now we're stuffing more numbers of moles of gas in there, but if we're looking at the partial pressures or the concentrations of our reactants or products, let's look at a reactant. The number of moles of the reactant aren't changing. the volume of the container isn't changing, which means the concentration of that reactant isn't changing. Now, the mole fraction is changing, but the concentration in terms of volume isn't changing. The partial pressure of that reactant won't change. Again, the total pressure of our whole gaseous mixture changes, because that increases as we stuff more gas molecules in. But the pressure due to that reactant won't change any. And this means that adding an inert gas doesn't affect the equilibrium position. When the volume of the container is changed, the concentrations and the partial pressures of the reactants and products change, if they're gases. And this means that changing the volume of the container will alter the equilibrium position. So when the volume of the container is reduced, the system responds by reducing its own volume, or attempting to reduce its own volume, which means that this is accomplished by decreasing the total number of gas molecules in the system. So the equilibrium will shift towards whichever side has fewer gas molecules, or of smaller volume. Because liquids and solids usually have much higher densities than gases do, that means they have much smaller volumes per mole, so they have much smaller molar volumes. They can essentially be ignored, and so if you have some reaction that turns, say, 5 moles of gas into 3 moles of gas, if you decrease the volume, so you increase the pressure, you can the system will then shift to the right, because it's going to shift towards the side with fewer numbers of moles of gas molecules. If you increase the pressure, if on the other hand you expand that system, it will tend to try to produce more gas molecules, and so it will shift to the left, changing the 3 moles of gas into 5 moles of gas. So note that the ideal gas law can be rearranged to give us this expression, where we have volume is equal to RT over P times N, the number of moles. So suppose we have an equilibrium mixture of nitrogen, hydrogen, and ammonia. If we reduce the system's volume, how will the equilibrium position change? The system will reduce the number of gas molecules present via the reaction. So we can go from the 3 plus 1 moles of gas on the left, so 4 moles of gas on the left, down to 2 moles of gas on the right. And that means that the equilibrium will shift towards the right. So again, since the left side of the equation contains 4 gas molecules, but the right side only contains 2 gas molecules, the equilibrium will shift to the right to reduce the volume, and we'll get more of our ammonia. But on the other hand, if we increase the system's volume, then the equilibrium will shift to the left to try to produce more gas molecules to occupy that extra space. So this means that increasing the pressure, not via addition of an inert gas, causes the equilibrium to shift towards the side with fewer gas molecules. And decreasing the pressure, again not via removal of an inert gas, causes the equilibrium to shift towards the side with more gas molecules. So note that changing concentration or pressure does not change the value of the equilibrium constant. But if we change the temperature, we do change the value of the equilibrium constant. So let's look at the effects of changing the temperature. So let's re-examine the synthesis of ammonia. We have the hydrogen plus nitrogen react to yield the ammonia, and now I've added in this plus 92 kilojoules. So we get energy out as we move from left to right. So recall that heating this system causes the concentration of ammonia to decrease, which means that increasing the temperature caused the equilibrium to shift to the left. And that is because we can essentially treat energy here as a product. So if we increase the temperature, we're increasing the available energy, the available kinetic energy. So we're increasing the concentration. You could think of it this way. We're increasing the concentration of a product. Well, Chatelier's principle says we should shift the equilibrium to the left. That is in fact what we see. So again, increasing the temperature requires adding energy. As more energy is added, we are effectively adding one of our products, and adding a product causes the equilibrium to shift to the left, away from that product. So that means that the value of K, our equilibrium constant, changes with temperature. And over here, we see for various temperatures, the value of the equilibrium constant for the synthesis of ammonia. And so you can see that the value of the equilibrium constant decreases as we increase the temperature. As if the value of the equilibrium constant is decreasing, that means that we are getting less and less of our product. That means we're shifting the equilibrium farther to the left, so it matches what we expect to see from Le Chatelier's principle. So let's look at one more reaction. So we have here N2O4 dinitrogen tetroxide in equilibrium with nitrogen dioxide, NO2, and the enthalpy change there is 58 kilojoules. So how will each of these changes affect the equilibrium position? If we add some more N2O4, how is that going to change things? If we add NO2, how is that going to change things? I want you to pause the video and think for yourself what effect these will have. So if we add some more N2O4, we're adding a reactant, we will shift the equilibrium to the right. If we add some more NO2, we're adding a product, we're going to shift the equilibrium to the left. So now we have a few other changes we can make. We can remove some N2O4, we can remove some NO2, we can add some helium, we can decrease the volume of the container, we can increase the volume of the container, we can increase or decrease the temperature. Again, I want you to pause the video, figure out for yourself which direction you think the equilibrium is going to shift in each of these cases. So, if we remove the N2O4, we're removing one of our reactants, we're going to shift the equilibrium to the left. If we remove the NO2, we're removing one of our products, we're going to shift the equilibrium to the right to produce more of that product. If we add helium, we're increasing the pressure by adding an inert gas. The helium isn't involved in the reaction. We're not changing the concentration of the nitrogen, the dinitrogen tetroxide. We're not changing the concentration of the nitrogen dioxide. We're assuming here that we're keeping the volume of the container constant, which means adding helium does absolutely nothing. It doesn't shift the equilibrium to the left or the right. It doesn't influence the equilibrium at all. Right? What happens if we decrease the container volume? As we decrease the container volume, the pressure increases, the concentration of dinitrogen tetroxide increases, the concentration of the nitrogen dioxide increases. But remember, as we increase the pressure by decreasing the volume, we're going to tend to shift the equilibrium towards the side with fewer gas molecules. Well, the left side, the reactant side, has fewer gas molecules, so that will shift the equilibrium to the left. Conversely, increasing the container volume causes the equilibrium to shift to the side which has more gas molecules. That's the right side. So we're going to produce more of our products. We'll shift the equilibrium to the right. So now let's look at increasing and decreasing the temperature. So remember that I told you that the enthalpy change was 58 kilojoules, which means that in going from the left side to the right side, from the reactants to the products, we have an increase of 58 kilojoules. If it were a decrease, we'd have a negative sign here, but we don't have a negative sign. We have a positive sign. So that means that the right side has more energy than the left side, which means that we have to put in energy to get this process to happen. So that means that over here, on the reactant side, we have energy as one of our reactants. So if we increase the temperature, we're adding energy to the system. So we're adding a reactant. If we add a reactant, Le Chatelier's principle says that we should shift equilibrium to the product side, to the right. And if we decrease the temperature, we are removing a reactant, and thus we should shift equilibrium towards the left. So that was Le Chatelier's principle.